Hello everyone, welcome to this presentation. My name is Ishas Kulkarni and I'll be representing our team today. The topic for our research today is an empirical evaluation of the energy consumption of using web push APIs in mobile apps, which specifically considering the case of Telegram. This is in collaboration with the Software and Sustainability Research Group of the Vrije Universiteit of Amsterdam and the Connecting Education and Research Communities for an Innovative Resource Aware Society group. As a part of this presentation, today I'll be going through the motivation for our research, the study design, the experiment execution, wherein I'll briefly talk about the experimental setup, how we executed the experiment, various constraints associated with the experiment. Furthermore, I'll be talking about the experimental results that we got after performing the empirical analysis, followed by a brief discussion towards the end based on the results. To begin with, we start with the motivation of our research. One of the primary motivation factors for our research is the extensive use of push notifications on smartphones today, which are regularly seen on mobile devices currently. Push notifications basically have evolved from being plain text to images to more complex type of media like hyperlinks being pushed to the mobile devices from the cloud. During the early days before mobile web applications became popular, long polling and WebSocket were the primary solutions for sending push notifications, which were ideal for scenarios that require persistent connections such as instant messaging. However, using WebSockets has a one limitation that it requires a full duplex TCP connection to be established during the complete session, while long polling requires a persistent connection between the client and server as well. In order to overcome these limitations, web applications have evolved to be progressive web applications, which are abbreviated as PWAs, as you see in the slide. PWAs allow web applications to send push notifications like native apps using the web push API embedded within the PWAs. PWAs are web applications that give users experience similar to native apps with better performance regardless of the device or the browser used for the mobile app. The web push API helps send push notifications asynchronously from the server to a web application. The figure that we see here depicts how push API mechanism works in PWAs. The process begins with the web page registering a new service worker with the user agent and with the subscription of the user agent to the push service. The resulting push subscription then produces a unique push endpoint, which is used by the application to subscribe to the server. When the server dispatches a push message, the message traverses the push service and then gets routed to the active service worker. In case the active service worker is inactive, the push API has the ability to awaken it to facilitate message delivery. After reaching the service worker, the push message is then presented to the user. Furthermore, in this particular diagram, we also see the push unsubscription mechanism, which closely resembles the subscription process. At the end of it, the push unsubscription mechanism removes the subscription from the application server and the push service eventually. Moving on, we briefly talk about the various factors that motivated the research questions for our empirical evaluation. The comprehensive literature study that we performed revealed that using WebSockets or receiving push notifications using PWAs might potentially negatively impact battery consumption in mobile devices. However, none of these studies comprehensively provide an answer to the question of to what extent adoption of PWAs for sending push notifications might impact energy consumption of mobile devices. This clearly shows a gap in the existing literature, which basically motivated our main research questions. As our subject, we selected the Telegram app considering its popularity with an estimated 900 million users worldwide And due to the fact that Telegram is one of the few apps that exposes various APIs to control the sending of push notifications for its web application. Considering these factors, we base our research questions. Our research question aims to mainly assess the implications of using Web Push API for the energy consumption of mobile web apps. Moving on, we base our research questions. As a part of the study, we have two main research questions, with each having sub-research questions on the basis of which we design our study. The first research question is, how does the enabling of push API affect the energy consumption of Telegram mobile web app? The sub-question to this main research question is research question 1.1, which says what is the impact of using different browsers on the energy consumption of Telegram mobile web apps. Next, we have our research question 2, which is mainly what is the impact in terms of energy consumption on receiving notifications with different sending patterns. The sub-questions for this research question are, what is the impact in terms of energy consumption on receiving notification with different sending frequencies? This could be messages sent in different frequencies, such as, for example, 5 messages per minute or 30 messages per minute or 0 messages per minute. Coming to the next and the final sub-research question, which says that what is the impact in terms of energy consumption on receiving notifications with different sending distribution patterns. In this, we concentrate the message sending distribution at shorter intervals, such as zero point 0.2 seconds interval as a distribution pattern, and we see the effect of this on energy consumption. Moving on, we move towards the study design of our experiment. Our experiment consists of mainly 4 factors and combinations of treatments applied to each factor. The independent variables for our experiment are the push API activation status, which could be enabled or disabled, the type of browser, which is in our case mainly is Chrome and Firefox. Next is the message sending frequency, which refers to the different rates of messages sent over per minute to the mobile device. And finally, we have different message distributions, in which we concentrate the messages in shorter intervals, such as 0.2 seconds per minute, per 0.2 seconds or 10 seconds per minute. And the dependent variable that we have as a part of our study is the energy consumption mainly. Moreover, for the message sending frequency distribution pattern of push notification messages, we have set up different levels in our experiment. For the message sending frequency, there are 3 levels mainly that are idle, low, and high. In the idle level, there are no incoming messages to the mobile device. In the low sending frequency, the incoming message rate is 5 messages per minute. For the high message sending frequency is the incoming message rate of 30 messages per minute. Similarly, for the distribution pattern of push notification messages, there are 2 levels we have set up in our experiment, which are burst and even. In case of burst, messages are concentrated over a short period of 0.2 seconds, and for even, the messages are evenly distributed over a period of 10 seconds. Based on this information that we discussed, we formulate our hypothesis. Now, I will briefly go over the hypothesis of our empirical study. We have defined the hypothesis for each of the research questions that I previously mentioned. For the sake of time, the hypotheses are clubbed together here for each of our research questions. To begin with, we have the null hypothesis, which states that there is no difference in energy consumption on trying out different combinations of the independent variables. On the other hand, we have alternative hypothesis, which states that there is a difference in energy consumption on trying out different combinations of independent variables that we discussed in the last slide. From here on, we move on towards the experiment execution and basically our experiment setup. For the experiment setup, we use a Google Pixel 5 device running on Android 13, on which the Telegram web application is installed and it's run there. Furthermore, we use Android Runner on a Raspberry Pi 3B to orchestrate the experiment. Android Runner is basically a tool for automatically executing measurement-based experiments on native and web apps running on Android devices. Within Android Runner, we use the battery manager profiler to measure the energy consumption of the Telegram web application accurately. Furthermore, we have written a Python script which is executed on the Raspberry Pi. What this script does is this makes use of the Telethon library of Python to send messages to the Telegram web app. Telethon is basically a Python library to interact with Telegram API, which is open source library. As a part of this experiment, there were a few constraints that we set up to avoid any erroneous readings. So as a part of this experiment, throughout the experiment, the mobile screen has been set up to remain locked and deactivated throughout to replicate a real life instance. Furthermore, notification settings in the phone are configured to only accept notifications from the browser to minimize energy consumption from other apps of the phone. The automated Python script is run with altered values with multiple trials for the experiment to get good accuracy. Next, we move towards the results that we obtained after performing this experiment. For the research question 1 and 1.1, we performed the normality check and got the result that the data that we collected is not normally distributed. Therefore, for the research question 1, which is for enabling push API with different notification statuses, may be enabled, disabled with Chrome and Firefox browsers. And for the RQ1, which is the research question 1, we performed the Wilcoxon signed rank test and we got a p-value which is less than 0.05, which indicates that the energy consumption for different notification statuses is significantly different. This is also evident from the box plots that we see here. And considering this, we can reject the null hypothesis in this case. Similarly, for the R research question 1.1, which is the first, the sub research question for the first research question, which is for different browsers, mainly Chrome and Firefox, if there's any energy consumption difference between the two. For this as well, we perform the Wilcoxon rank sum test and conclude that the p-value is again less than 0.05, which indicates that the energy consumption for different browsers is different. This also can be observed from the box plots shown here. Therefore, we can reject the null hypothesis for this. The box plot for this is mainly in the previous slide, which we can see here. And in this slide, when we look at the distribution of the received notifications from these box plots, from both Chrome and Firefox tend to consume less energy when receiving the notifications in burst. This can be seen from the box plots here. And Firefox over here shows a more pronounced effect as compared to Chrome as seen here on the right hand side. And now for the research question 2 hypothesis tests, we perform the Wilcoxon ranked signed rank test again for Chrome browser with different message sending distribution patterns. The p-value is greater than 0.05 as seen in the table here. And thus we can accept the null hypothesis for Chrome browser with different sending distribution patterns. However, for Firefox, the p-value as we see here is less than 0.05, and hence we need to reject the null hypothesis, and thus we can conclude that there is a slight difference on energy consumption on Firefox browser with different sending distribution patterns, whereas in Chrome there is almost no difference. Coming to the different message sending frequencies for Chrome and Firefox, we get a p-value less than 0.05. Hence, we can reject the null hypothesis as we can evidently see in the table here and also in the box plots corresponding to sending frequency for both Chrome and Firefox browsers. That is, this is applicable, and thus we can reject the null hypothesis in this case for the different sending frequency of messages. These were mainly our results. As a part of we move towards the discussion section, and as a part of the discussion section, our primary findings from the results that we obtained are as follows. Enabling push notifications in Chrome and Firefox has a shows a significant increase in energy consumption on both the browsers. Moreover, Chrome generally exhibits higher energy consumption than Firefox, regardless of the notification status, whether on or off. The distribution of messages for even or burst distribution has very minimal influence in terms of energy consumption, as we saw in the box plots in the previous slides. Significant distinctions are present in terms of energy consumption concerning push notifications with different frequencies, as we evidently saw in the previous slides here, where we see the differences. And this concludes basically our discussion and our basic findings from this. That's all I have for now. Thanks a lot for listening.